Hey guys, so here's the first video in a series of videos that's going to cover review for the AP exam. If you look at your notebook should have the page titled Unit 1 Atomic Structure and Properties. All right, this will give you an overview of everything that's going to be covered in the unit. All right, and then when you click on the drop down arrow, I should have everything already set up for you in unit by unit. So unit 1.1, 1.2. The first page is always going to be like the essential learning objective, what it is that we're going to be covering. And then it's going to be a series of notes with some practice prompts so you can see what to expect on the AP exam. Now, I'm not going to lie to you guys. Most of this stuff is from College Board. Okay. I'm putting it to you guys this way. So I'm hoping to see if maybe I can explain it a little bit more clearly. But don't make a hero out of a saint for me. I don't have a textbook for you guys. So this is about as best as we can do. But we're going to go ahead and go through this, and I'm going to split it up into two parts. So you're not sitting here drudging on through an entire 1 hour and a half video or something like that. I'm going to try and make it as painless for you guys as possible. Okay, so the first unit that we're going to cover is unit 1.1, and that has to do with moles and molar mass. Some of these units, guys, they're pretty simple, some of the earlier ones. So I'm not going to spend a whole lot of time on these because most of these you should already know, especially after taking 2 years of chemistry. So when we're looking at something like moles and molar mass, right? And basically what we're doing is we're trying to identify the relationship between moles and mass. So if we take a look at a very common, let me take a look here. Very common element, the one that's used for a whole lot of things, is carbon. And we're all carbon based. So let's take a look at carbon the way it looks on the periodic table. Okay. All right. So if you take a look at carbon, carbon is element number 6 on the periodic table. It's got a chemical symbol of C, and you can see that it has an atomic mass of 12.01. Well, the mathematical relationship that they're trying to explain here is that you know that this is the atomic mass, okay? And the atomic mass is simply the mass of 1 mole of the substance. So 1 mole of carbon, carbon is equal to Avogadro's number, right? In atoms. And what it's saying is, if you were to get this many atoms together of carbon, right? It's a huge number. If you were to get this many atoms of carbon together, then those atoms, or 1 mole of carbon, has a mass that you can actually measure at 12.01 grams. Now you can round that just to 12.0, and that's exactly what they've done here, right? So 1 mole of carbon has a mass of 12.0 grams, all right? Basically, all these are, guys, is just the atomic masses from the periodic table. So this is equal to the atomic mass, all right? And that's pretty much it. You guys already know this, all right? But when it comes to doing molar mass, right, 1 mole, what it's saying now is that 1 mole of NaCl, right, is equal to the mass of sodium, right, plus chlorine. And both of these have to do with the atomic mass, right? So if you're going to find the molar mass of something, right, then you would find the molar mass of sodium, right, which in this case is 22.99. So sodium is equal to 22.99. Chlorine is equal to 35.45. Okay, and if you add those together, 22.99 plus 35.45, you should end up right around 58.44. Right? Grams per 1 mole. Right? That's pretty much it. Remember that molar mass is just the sum of the atomic masses of each individual element, right? That's in the periodic table. So let's go ahead and screw this over a little bit here. And then I'll put here molar mass is equal to the sum of atomic masses. In a compound. Okay, that's pretty much it. Okay? If you do something more complicated, like sucrose, for example, the chemical formula for sucrose is C12H22O11. First, you got to do is you got to find the atomic mass of each element, right? Carbon is 12.01, hydrogen is 1.008, oxygen is 15.99. These are all, I want to forget, these are all grams per mole. See if I can get my pencil here to change color, right? These are all grams strange, not writing. Oh, now I want to write. These are all in grams per 1 mole, okay? So just remember that. This is grams per 1 mole, okay? So we have the atomic masses, okay? Then we multiply each one by the quantity. So you take a look at these numbers. These are the subscripts that tell you, right, how many of each you have in the compound. Okay, so we multiply 12 times 12.01 times 12. We multiply 1.008 times 22, multiply 15.99 times 11, and we end up with an atomic molar mass. Okay, so this is equal to your molar mass. And that's it. Let's go ahead and move on to unit 1.1, mathematical relationships, and do some practice here. All right, so when we're talking about conversions, right? Grams to moles, moles to grams, atoms, whatever. We use conversion factors, okay? Conversion factor is just a ratio or fraction that shows you the relationship between the same amount of something in two different units, okay? So there are two possible conversion factors for each quality, and I'll tell you what that means in just a minute. But the conversion factors that, that can be used, basically all we're doing is using them to convert from one unit to another. And that's going to be usually from moles to grams or grams to moles. Okay. So when we're taking a look at the conversion factor, and this is what I wrote earlier, right here, the 1 mole of carbon is equal to 12.0 grams of carbon. You can write that either way. You can say, or you can say that 12 grams of carbon in 1 mole of carbon. Right? It's pretty much the same thing. And that's exactly what we're showing here, right? You can write it in two different ways, but they're both correct. All right. What I want you guys to remember is that the format that we're going to use is going to be here. Okay. Your starting unit is always going to be over 1. That's how you're going to set it up. And then you're going to multiply by the conversion factor. What I want you guys to remember is that whatever unit you have here has to be the same unit you have here. So when we do this, that's why we have two versions. You have to see which one of these is going to align with the starting unit. If your starting unit is moles, for example, right, then you're going to use the one that has moles on bottom, right? That way you cancel out. If it was grams, then you would switch it the other way. Okay. So a sucrose packet contains 4 grams of sucrose, which is C12H22O11. That's exactly what we calculated in the previous slide. How many moles of sucrose does a packet contain? Well, first we got to know what the molar mass is. Now we've already calculated that, right? It's 342.3 grams per mole, or you can say that 1 mole of sucrose is equal to 342.3 grams per mole. Okay. Now we're going to use that and we're going to convert that, right? We're going to convert that. All right. We have the same setup. Okay. So if we have 4 grams of sugar, right, we're going to put that over 1, just like we did here. And then we got to figure out which one of these conversion factors we're going to use. So in the example that's already been done for you, you can see that if you have grams at the top, you need to make sure you have grams at the bottom, right? Because what happens is those grams cancel out and you're left in moles, which is your desired unit. If you multiply straight across and you divide at the end, you end up at 0.012 moles of sucrose in 4 grams of sucrose or sugar packet, right? And that's all it is, guys, is the molar mass is the conversion factor that we use to convert from grams to moles or moles to grams, okay? That was unit 1.1. Pretty simple. Most of this should be review. It should be pretty easy, all right? Now, here's something that we're going to talk about, which is the mass spectroscopy. I haven't gone over this in class, but it's basically taking all the stuff I have gone over in class, all the stuff that I've already taught you, and just applying it in a slightly different way. So I want to make sure you guys see a couple of these problems because you're gonna see some of these on the exam, and I want to make sure that you guys are prepared. Okay, so let's talk about first what a mass spectrum is. I'm going to scroll up to the top here. So mass spectroscopy, okay, is pretty much a breakdown of an element. Okay, so basically it's a technique used to identify the isotopes of an element and their relative abundance in nature. Now, this is not new. We said before that elements are made up of different isotopes, right? So an isotope, remember, okay, an isotope, let me put it over here. Is the same element with a different number of neutrons. All right, because it has a different number of neutrons, those isotopes exist in different abundances. Okay, now when you take all those abundances together and you combine them is how we calculate the average atomic mass. So to answer the question is, how do we get this atomic mass? Well, it's the sum of all the isotopes. Of an element. Okay. Now, I don't know if you guys see this or not. My screen kind of keeps flashing on and off. I hope you guys are not getting that, but that's what I'm seeing on my end. Okay. So let's take a look at an example of a mass spectrum of chlorine, right? So chlorine has 2 isotopes, okay? Each bar represents a different isotope and the graph has 2 bars, okay? That's what it says right here, see? All right, so in the blue box, it says that the mass of one isotope is 35 U, which is atomic units, which is Cl35. And the other isotope is 37 atomic units, which is Cl37. So here's what it's saying, okay? When you look at a mass spectrum graph like this, each one of these bars is going to represent an isotope. So this is one isotope. And this is one isotope. Okay, so each one of the bars represents a single isotope. Okay? Now, if this graph had 4 more bars, for example, then you would say that this element has a total of 6 isotopes. In this case, chlorine only has 2. Now, across the bottom, you're going to see that there's a number there, okay, 35 and 37. That means that one isotope has a mass of 35 atomic units or grams per mole, and the other one has a 37. Remember, isotopes have a different number of neutrons, and since most of the mass of an atom is in the nucleus, then a different number of neutrons is going to have an effect on the molar mass or on the atomic mass. So just remember that. Nucleus, more neutrons will change mass. Now, most of the mass is in the nucleus, okay? But we can only change neutrons. If you change protons, then you're changing the element completely. Remember, an element changes from one element to another by the addition of another proton. So if I change the number of protons, well, I'm no longer chlorine, right? If I add another proton, then I become argon, right? So just remember that an isotope is same element, same number of protons, but you have a difference in the number of neutrons, okay? And that difference of the neutrons is going to affect the overall mass. Now, the numbers on the side here is the abundance, right? The abundance. For example, this one is about sitting right around, say about 75%. So 75% of all the isotopes, right, in chlorine are going to be chlorine 35. You look at this one's sitting right around about 25%. Okay, so these are what we call the percent abundance. Okay, so 75% of all the isotopes are going to be chlorine 35, and 25% of them are going to be chlorine 37, right? So how do we calculate the average atomic mass? Well, to do the work, you basically have to just multiply, okay, the mass of the isotope, and you're going to multiply that by the amount of percent abundance. Of course, you're not going to multiply by the percentage, you're going to multiply by the decimal, but if you take 35 and we multiply that by 0.0 or 0.75, sorry, you're going to get, let me see here, 26.25. Then I'm going to take 37, right? I'm going to multiply that by 0.25. We get 9.25. And if I add those together, I'm going to get 35.55 or 35.5. Okay. And this is exactly rounded, of course, the atomic mass of chlorine. So this is your average atomic mass. Okay. And that's how it's calculated, guys. That's how you calculate the average atomic mass of an element. You add up all the isotopes of an element, then you bring them together, you take the sum of their percent abundance, and you can calculate the average atomic mass. So when you're looking at a mass spectrum, this is what it's going to look like. It's just going to be a series of bars, and they're going to give you the mass and the percent abundance across each axis, okay? So the here, and this is exactly what we just did. The height of the bars here represent exactly what we just did, 75%, 25%. Okay. This could be the other thing about the mass spectrum is it can either be mass, it can be mass per charge, or mass number or atomic mass. Okay. You just have to pay attention to what it is. All right. The work's not going to change much, but you just might see a slightly different unit. All right. So here we have another example of a mass spectrum. Okay, let's take a look at this one and see if we can figure out what the element is. This one is for you. I want you guys to go ahead and pause it for just a second and then try and work it out. Okay, remember that these look like they're increasing by a factor of 0.02. Okay, or 0.2, excuse me. And then see if you can figure out what element this is. All right. Okay, so let's take a look here. Okay, guys. So this is something that that is going to be something similar on the test. I went ahead and I didn't want to take too much of your time. So I went ahead and just kind of listed what the values were at each one of these bars. And these are, guys, these are just approximations, okay? Remember that these are in point, 0.2 increments, okay? So you just kind of have to go in there and ballpark it as close as you can. For example, this one right here is a little bit less than 0.1. It's more than it's right at the line. So I'm gonna say this is about let's see, 0.080, give or take, right? And that's all you have to do. That's all you have to do, right? Just take your best guess. It doesn't have to be exact, but try and get it as close as you can. This one right here was the one that was kind of a little bit, was a little bit tricky. It's not right at the line. So the value that I picked for this one, I picked 0.238 because it's not quite at 0.240. This is 0.09. This is 0.078, okay? And this one is 0.5. That one's actually the only one that's actually pretty darn close. So I'm gonna go ahead and list these right here, okay? I'm gonna start from the very left. So it's gonna be 0.09 times 76, right? That's the mass. Then it's gonna be 0.079 times, 78 times 77, right? It's going to be 238, sorry, times 78, 0.5 times 80, okay? And then the last one is going to be right around 0.080, and I'm going to multiply that by 82, all right? So once you get all these numbers, guys, okay, and you add them all up, okay, you should end up somewhere pretty close to 79.2, okay? Now, if you look at the periodic table, there's two elements that this could be, right? You got selenium, which is sitting right around 78.96. And then you got the one next to it, which is bromine, which is sitting right around 79.9, okay? Now, if you go before selenium, you have arsenic, right? Arsenic is sitting right at 74.92. So obviously it's not gonna be arsenic, right? So now you're left between bromine and selenium. Remember that you're gonna have rounding error, okay? So just pick the one that it's closest to. In this case, it's gonna be closer to selenium, okay? So if we scroll down a little bit, all right, we can see, we can say that this element here would be selenium, okay? Is it gonna be exact? No, it's not gonna be exact. You can try and wait to round at the end and kind of just see where you end up. But most of the difference, guys, is gonna be in rounding error, and it's gonna be on this. I see 0.078. Some of you guys may say, you know what, mister, that's closer to 0.076. So long as you're close enough, you should get the right answer, okay? But the moral of the story is, in order for you guys to figure out what element this is, you should be able to kind of give yourself a pretty good chance by understanding how to calculate average atomic mass, which is just the abundancy times the mass added together. All right. Let's go ahead and practice a little bit here. Scroll all the way to the top. So mass spec on the exam, you're going to see three basic types. Okay, you're going to have to estimate the atomic mass from a mass spectrum. This could be a fake element. Identify the element from a mass spectrum, like we just did, or identify the isotope from a mass spectrum. Okay, identify the isotope. So let's take a look at the first one here. So the average atomic mass of chlorine, that's actually exactly what we just did in the last one. Okay. So I want you guys to just kind of work this out and see if you can do it without looking at the notes. Okay, let's try this next one. It says here, which element spectrum is shown on the graph at the right? Okay, this is another one of those. It's going to be, you just kind of have to take a look at it. It's between 39 and 41. So what I see here is that this is an isotope. Okay, this is an isotope. and this is an isotope. So this element has 3 isotopes. That's what we got here. Okay, so already we can see that it has 3 isotopes. Now, the first isotope has a mass 39, mass charge of 39. Next one is 40. Next one is 41. So you're going to see you're going to be somewhere in that ballpark. Okay, so let's take a look and see if we can figure out what element this is. Okay, so I went ahead and filled in the values here. All right, like I said, I don't want to take too much of your time. So looking at this here, we can clearly see that this is right around 90%, maybe even more. Remember, guys, that percent isotopes have to add up to 100. So if we're going to say that this is 90%, give or take, right, then these two guys have to be somewhere in between 10%. So this will be 0.07, this will be 0.03, and that should get us right to 10%. This is not exact, it's a ballpark. It's a ballpark, but you got to do the best you can, okay? So at 90%, I'm going to multiply that value times the mass at that isotope, which is 39. So 39 times 0.9, that's going to give me 39 times 0.9. That's going to give me 35.1, 35.1. If I take the next one at 0.03, right, because if you see it's a little bit less than half. 0.03, I'm going to multiply that by 40. Okay. I'm going to end up with 1.2. And then the last one is going to be about 0.07 times 41. That's going to give me a value of, let's see, 0.07 times 41. That's going to give me a value of 2.87. 35.1 plus 1.2 plus 2.87. That gets me right around 39.17. Okay, 39.17. So this is the average atomic mass, or the AMU. Okay, so let's take a look and see what lands in that ballpark. We got argon, which is 39.95. We have potassium, which is 39.10. And then we got calcium, which is 40.08. Now, we're not going to get perfect, right? But we can get pretty close, okay? And for me, the answer is clearly potassium, okay? Argon's a little bit over by about 0.8, okay? And calcium is already in the 40s. So the answer for this problem would be that this element, or this spectra, right, is showing you the element potassium. All right. But even when you have a spectra, just understand that the bars represent the isotopes. You can use the percent abundance to give you a pretty good guess as to what the element is going to be. This is going to be pretty much the same thing, guys. This one just has more isotopes. So if you look at this graph, it's got 1, 2, 3, 4. This guy has 5 isotopes. 5 isotopes. Okay. It's going to be pretty much the same thing. We're going to ballpark it. Okay. So we're going to say that the first one is about 28. Let's see here. Sorry, 20%. Let's see here. Oh yeah, okay. So we're going to call it here 20%. Okay. Next one's going to be a little bit closer to 28. Okay. Let's call next one at about 8. All right. 38 for this guy. All right. And 5.32. I'm sorry. 7. Let's call this guy 7. All right. So looking at this, okay, I want you guys to go ahead and take a look and see if you can figure this one out. All right. I'm going to pause the video. I want you guys to pause the video, work it out, verify that I got pretty close with these, right? Because we're pretty much doing the same thing. And let's see what you come up with. Okay. So we're back, okay? Here's what we come up with. All we did was took the percentages that we thought they were, okay? Multiplied them by each atomic mass, okay? Then we summed them all up at the end and we ended up to be somewhere between 72.72, okay? So between 72 and 73. So let's take a look and see where we're at, okay? So here are the elements that are close. Gallium is 69.72. Germanium is going to be sitting at 72.63. And then the one after that is arsenic, which is sitting right around 74.92. Okay, so we're between 72 and 73. Obviously, the answer for this one is going to be germanium. Okay, that's all a mass spec is, guys. That's all the mystery between a mass spec. All you have to do is take a look at the bars, know the isotopes, ballpark it the close you can as the percent abundance, and then just calculate the average atomic mass. That's how you identify an element. All right. So let's go ahead and move on to section 1.3. Please, guys, feel free to stop the video. Make sure to put this in your notes and pause and rewind as you need to. Okay, so section 1.3 is going to be elemental composition of pure substances. Okay, so let's go ahead and take a look at this one here. Let's scroll up. I keep forgetting to scroll these guys up. So when we're talking about a composition of pure substances, basically all it's saying is that they have a fixed composition. It means it's all the same across the board, right? So it means all the same. Okay. The elements present and the ratio of those elements is the same for every sample of the compound. So if I have, a sample of salt on one hand, and I get salt from a different source, they're both going to have the same chemical composition. They're going to both have the same ratio of atoms, 1 sodium to 1 chlorine, just like we have 2 hydrogens for 1 oxygen and a ratio of 2 to 1 for water. And all water is going to exhibit that same ratio, 2 to 1 ratio. All salt is going to exhibit that same 1 to 1 ratio. And the chemical composition is going to be identical whether I get water from a sink in Canutillo or if I get water from sink in my house. Water is water, right? So that's what we're looking at when we're talking about a pure substance, okay? Fixed ratio. Now, when we're looking at sodium chloride, right, 39.34% of sodium chloride is sodium and 60.66% of that is chlorine. And this is the percent by mass, okay? So this has to do with percent composition, all right? Percent composition. So remember that, okay? And basically that's what it is, guys, is the percent composition is gonna be pretty much the same across the board, no matter where you get your salt or no matter where you get your water, okay? It's always gonna have right around this percentage, if not exactly that, okay? And that represents the percent composition of each atom in the given compound. So how do we find percent composition? Well, let's take a look at sucrose, right? Here's an example that's already been done for you, okay? Basically what we have to do then is we have to take the mass of the element. We have to figure out how many of each element are in the compound, right? For sucrose, here's the chemical formula. This gives you the quantity, right? So we have 12 carbons, 22 hydrogens, and 11 oxygens, okay? Then we're gonna find their atomic masses. These are the atomic mass from the periodic table. Okay, we're going to multiply that, we're going to add everything together, and we're going to find the average atomic mass. So this is the this is molar mass. Molar mass of sucrose. Now, if you want to figure out the percent of each element in the compound, then what you're going to do is you're going to take how much of each element you have. For example, in sucrose, 144 of those atomic mass units are made up of carbon. So I'm going to take the 144 of carbon, okay? Then I'm going to divide it by the entire molar mass, right? I'm going to divide it by the entire molar mass. Again, this is all review. This is our review, right? There it is. I'm going to do that for each successive element in the compound, and then I'm going to multiply those answers by 100, and that's where I'm going to get these percentages. So we can see that sucrose is 42.1% carbon, 6.49% hydrogen, and 51.40% oxygen. Okay, that's pretty much it, guys. Again, this is something that we've done in class countless times. Percent composition is just the mass of the element in the compound, the total mass of that element, divided by the total mass of the compound. Okay, let's do a little bit of practice here. We have a compound that is nitrogen and oxygen. The name of this compound will be dinitrogen tetroxide. All right, and what we're going to do then is we're going to calculate the average atomic mass. All right, I mean, we're going to calculate the percent composition by mass of these guys, but first we had to find the atomic mass. So I have nitrogen and I have oxygen. Okay, nitrogen has a mass of 14.007. 0.007, correct. Okay, and oxygen has an atomic mass of 14.9994. Okay, I'm going to multiply by the quantities that they have in the compound. So this is going to be by 2. This is going to be by 4. And let's calculate those products. Okay, 14.007 times 2 is going to give me 28.014. Okay, 15.9994 times 4 is going to give me 63.9976. Okay, I'm going to go ahead and add these guys up. That's going to give me a total mass of 92.0116. I only have 1, 2, 3, 4, 5 significant figures. 1, 2, 3, 4, 5. So this is going to be 92.012 grams per mole. So this is the total molar mass, okay, of the compound. Now, if I wanted to get the percent composition of each one, then I would take nitrogen is equal to the total mass of the nitrogen in the compound, 28.014. Remember, this is the of it in the compound, not the atomic mass. Then I'm going to divide that by 92.012. Multiply that by 100. And I should end up with, see, 28.014 divided by 92.012 gives me a total of 30.45%. Okay, so this is nitrogen. Okay, we use a different color here. Now I'm going to do oxygen. Oxygen, I'm going to scoot this over a little bit, guys, just so we have a little bit more space to work. Remember, you can always capture this from my screen. You don't have to copy everything down unless you want to. It helps you remember better. Oxygen is 15.9994 divided by the total mass, which is 92.012 times 100. So that's 15.9994 divided by 92.012 gives me a total of 17.4%. Oxygen, so we have that. And then if that doesn't work, remember, you can always just take the percent of nitrogen, which is 30.45%, and then subtract that from 100. Oh, see, even I made the mistake. Should add up to 100. So it's not 15.994. I was like, why isn't this working? It should be 63.996. 63.996. Let me go ahead and erase this. Divided by 92.012. All right, that gives me 69.55%. Sorry, guys, it's almost 7 o'clock. Okay, for oxygen. So if I do the same thing, 100 minus 30.45, I get 69.55. Right? Remember, because the percent composition has to add up to 100%. So you can do it either way. You can do it either way. Okay. But that's pretty much it, guys. That's pretty much percent composition in a nutshell. When you're looking at a percent composition, okay, there's certain times when you're going to see when we start getting into empirical and chemical formulas. Okay. Here's an example of a compound that is two different compounds, but they have exactly the same percent composition. Now, in this case, the reason that happens is because this one happens to be the empirical formula of the compound we just did. So even though the mass is going to be different, because the ratios are still the same at 1 to 2, you're going to end up with a compound that is the same percent composition as another compound. So when you see a question that says something along the lines of, can two different substances have the same percent composition? Well, yeah, absolutely. Because the percent composition is made up by the ratio. And if you're taking the empirical formula and the chemical formula, those ratios shouldn't change. And if the ratios remain the same, even though the mass is different, you should end up with the same percent composition, okay? Now, the difference between a molecular and an empirical formula is going to be pretty simple. It's just whether or not something can be reduced, okay? Can you take the formula and all the subscripts that we see here, right? And can you reduce them to a simpler form, okay? In the first example of formaldehyde, CH2O is already at its simplest form and cannot be reduced. So in this case, the molecular formula and the empirical formula happen to be the same. If you take a look at glucose, for example, glucose is made up of 6 carbon, 12 hydrogen, and 6 oxygens. If you can see that they have a common factor, I can reduce all of these guys, right, by at least, what, 3, right? Or no, by 6. I can reduce them by 6. So if you reduce these by 6, this becomes a 1, this becomes a 2, this becomes a 1. So in this case, the two empirical formulas for these two very, very different compounds are the same. But in this case, this is the empirical formula and the molecular formula are different. Can nitrogen dioxide be reduced? No. So those are going to have the same empirical formulas. Can dinitrogen tetroxide be reduced? Yes, it can. So here we see that two different compounds can share the same empirical formula, even though their molecular formula is going to be different. Okay. When we're talking about writing the empirical formulas, right? All you have to remember when writing the empirical formulas is, can it be reduced? If it can, reduce it. The simplest whole number ratio you can get is going to be your empirical formula. So you can see here that dihydrogen dioxide can be reduced to hydrogen monoxide. Sodium sulfate cannot be reduced any further. That's going to stay exactly the way it is. And then C2H4O2 can in fact be reduced to CH2O. So if you can see that these guys have a common factor, that you can reduce them, that's all you need to do to find the empirical formula. Okay, let's go on to some practice with empirical and molecular formula. Okay, you're going to see 3 types of empirical molecular formula on the AP exam. Straightforward mass or percent composition data, which is what we got a little bit ago. Combustion analysis, we're going to be burning a sample in analyzing products to determine the relative amounts of carbon and hydrogen. And then you're going to do a hydrate analysis, which is when you're heating up a hydrated ionic solid and analyzing the mass change to determine the mole ratio of water to anhydrous solid. That's a mouthful, I know. But we're going to do an example here in a minute that should help clear this up a little bit. All right, let's take a look. So we have a question here that says a 23.0 gram sample of a compound contains 12 grams carbon, 3 grams hydrogen, and 8 grams oxygen. Which of the following is the empirical formula of the compound? Okay, well, we have all the masses there, right? These are the masses of individual elements, right? So what we're going to do then, the first thing we need to do is we're going to convert everything to moles. We're going to convert everything to moles. So we have 12.01. Remember those conversion factors, we're going to divide it by 12, which is the atomic mass of carbon. We're going to take 3 grams of hydrogen divided by 1, and then 8 grams of oxygen divided by 16, rounded up, right? 15.999. And we're going to end up with these values: 1 mole of carbon, 3 moles of hydrogen, and 0.5 moles of oxygen. Okay, this is in your notebook. You should have this. We did this at the early beginning of the year. Okay, once we get there, we're going to divide each value by the smallest mole value. In this case, the smallest mole value is going to be oxygen. So I'm going to write that there, smallest mole value. Okay. And so we're going to take the 1 mole, all the moles that we got, 1 mole of this, 3 moles of that, 0.5 moles of this, and we're going to divide each one by 0.5. And that's going to give us these numbers. Okay. So then on the multiple choice, we have to figure out, okay, so our compound is going to be 2 carbon, 6 oxygen, and 1 oxygen. Which one is that one? Oh, there it is. There it is. Okay. Basic percent composition. This is something that you should already know how to do. Okay. It's getting close to 7 o'clock, guys. So I'm going to go ahead and stop the video there. I think the video's gone on kind of long. So I will pick up this one tomorrow, because I think I'm going to get kicked out of work here in just a minute. Okay. So this is the one we're going to do tomorrow. I'll go ahead and get it done for you guys. And if you have any questions, let me know.